another goal that we mentioned is robustness. So we want to know how well does the system perform in the presence of sort of undesired inputs and undesired model uncertainty. So measurement noise and disturbances are examples of unwanted inputs, and we want them to not adversely affect the response of our system, the behavior of our system. In essence, we want our system to not react to noise and disturbances. We also want to be robust to uncertainties in our model. So we've designed our controller based on some model of the plant, and we achieve a certain level of performance. We want that performance to not degrade if it turns out that the actual system is different than our model. So if there's a certain amount of uncertainty in the mass of a vehicle or the inductance of a motor, we want changes in those parameters to not have a large effect on the performance of the system, its speed, its overshoot, its steady state error, etc. And we also want the system to be robust to time delays. And so this isn't something we've talked about much, but we will talk about it in a little bit in more detail. But in essence, if we're using a sensor or we're using some information and it's delayed such that it's old by the time our controller tries to employ it, we want our system to still perform well. We don't want the delay in that information to degrade performance, to cause us to go unstable even. In general, there is a trade-off between robustness to these different sources. As is always the case, we generally cannot achieve all of our goals simultaneously. For example, we may not be able to make our system robust to both noise and disturbances at the same time. And we'll show a little example of this on the next slide. So let's consider this multiple input, multiple output system, this MIMO system. And we have three different external inputs. We have the reference R, we have a disturbance D, and we have noise N. And we want to react to these three different inputs in different ways. In particular, we want to attenuate disturbances and noise. We don't want to react to those inputs, those undesired inputs, but we don't want to attenuate the reference, the command that we're actually trying to follow. So let's go ahead and take a look at the closed loop transfer function for each of these three inputs to an output of y to try and better understand this situation. So for an input of r and an output of y, we have a negative feedback loop, and we can use our shorthand rule, forward over 1 plus loop. In this case, the forward path includes the controller and the plant, so the forward path is c times p. The loop is also c times p because we have a unity feedback system. Therefore, the transfer function from r to y is c times p divided by the quantity 1 plus c times p. If we look at the disturbance, we still have a negative feedback system. It's just that the disturbance enters in a different location. So the forward path in that case, from an input of d to an output of y, the only thing that's in the forward path is p. But the loop itself is the same. So the closed loop transfer function from d to y is p divided by the quantity 1 plus c times p. P is the forward path, c times p is the loop. Then if we look at an input of noise, and you look at the path from the noise to the output, the only thing that it includes is c and p, but you will also notice that this input passes through a summing junction with a negative sign. And since we handle one input at a time, i.e. we treat r as if it were equal to 0, when n passes through this negative sign, it's as if it's 0 minus n. So it's as if we're multiplying by a negative 1 when we go in the forward path. The loop, however, will be the same, And so then you see what we achieve. The closed loop transfer function from n to y is negative c times p divided by the quantity 1 plus c times p. So looking at these three transfer functions, you'll notice a few things. One, all three transfer functions have the exact same denominator. So that means the closed loop system for each of those three inputs has the same poles, presuming no pole zero cancellations. In fact, the transfer function from r to y and the transfer function from n to y are identical, except for the negative sign. And so right away you can see that if you desire to attenuate noise, you can't do that without also attenuating the reference. So here's an example of this limitation. So here you can see that the transfer function from r to y is equal to the transfer function from n to y, just with opposite sign. These two transfer functions are also related to the third transfer function, the transfer function from the disturbance to the output, as shown here. And so the takeaway is that these transfer functions are not independent. So if you do something in order to, let's say, attenuate the disturbance, you may adversely affect the system's response to noise or the system's response to the reference. Going a little bit deeper, let's go ahead and attempt to design a controller to attenuate noise and to attenuate disturbances. So for example, if we made the magnitude of our controller large, if we made C large, then for a disturbance, this magnitude of C is getting large, and let's say the magnitude of the plant, the process, is staying the same, then we have something that's getting very large being divided into something that's staying the same, and so the magnitude of the response of the output to that disturbance will get smaller and smaller and smaller. And in the limit you could make it approach zero. So making the magnitude of the controller large would make the system attenuate the disturbance completely. If we did that, however, what would the effect be on the system's response to noise? So if we made C very large, then this quantity would get large and it would dwarf the 1. And so you would get something of a large magnitude divided by something of an almost identically large magnitude. And so the magnitude of that transfer function would approach 1, since magnitude doesn't depend on sign. So here we see that we were able to attenuate the disturbance, but we weren't able to attenuate the noise. In fact, the noise is not attenuated at all. Its phase is shifted 180 degrees, but that doesn't really matter. What matters is that the amplitude of the noise directly affects the output. It's not attenuated at all. So let's try the other approach now. Let's try to make the magnitude of the controller small, make it approach 0. If we do that, looking at the transfer function from d to y, we make the magnitude of C very small, then the magnitude of this quantity will be small, and will basically approach P divided by 1. And so as we do that, the closed loop transfer function from d to y approaches the transfer function of the plant by itself. So what that means is, however the plant responds to certain inputs of a certain frequency, that's exactly how the closed loop will respond to disturbances. If we look at the effect on noise, if we make the magnitude of C small, then we get a small magnitude in the numerator, we get a small magnitude here, so we'll have something that's getting very small divided by something that's basically 1, and so the smaller we make C, the closer that transfer function becomes to 0. By inspection, we can see that making the magnitude of the controller small is good for noise, but not good for the disturbance. And if we make the magnitude of the controller large, that's good for the disturbance, but it's bad for noise. And so the lesson is, we can't attenuate both noise and disturbances at the same time, or at least not necessarily. So what do we do? Well, one solution is that we can rely on the fact that our systems respond differently to different frequencies. And so we can sort of take advantage of this and make the system attenuate noise in one frequency region and make it attenuate disturbances in a different frequency region. Specifically, we will attenuate noise at high frequencies, because noise tends to be high frequency, and we will attenuate disturbances at low frequencies, because disturbances often change slowly. So you could imagine, for a cruise control example, that a change in grade or a change in the mass of the vehicle will change very slowly, or a wind gust, the dynamics of that will be much slower than the frequency of electrical noise, for example. And so this is a strategy that will work well in many instances. And based on the previous slide, we saw that in order to attenuate noise, we want our controller to have small magnitude, and in order to attenuate disturbances, we want our controller to have large magnitude. So that means that we're going to try and achieve an open loop frequency response plot that has high gain at low frequencies, to attenuate disturbances, and small gain at high frequencies to attenuate noise. This sort of approach is also advantageous because we tend to have the most uncertainty at high frequencies. And we saw this a little bit when we had that example where we did the system identification of a power converter. The model was really jumping around at high frequencies, and you could imagine that might be the case because it's difficult to measure the phase very accurately when you're dealing with large frequencies. If you have a very small period, a small time instant is a very large percentage of the cycle. And so by attenuating the high frequencies, maybe we don't know what the model is doing very well, but if we attenuate it, then we don't have to worry about it as much. We're not sure what it's doing, but we're just going to attenuate it so that we don't have to worry about it.